From the dawn of human thought, the night sky has been a canvas of mystery. People once believed the heavens were a dome, a ceiling that enclosed our world. Later, with the invention of telescopes, we came to see that the sky was not an enclosing sphere, but an endless ocean of stars and galaxies. Yet even today, with all our advanced science, the question still remains: is there an edge to the universe? And if so, what lies beyond it? This question is not just scientific, it is philosophical, almost spiritual, for it touches the very boundaries of human understanding. But this does not mean that the universe has a hard edge sitting at 46 billion light-years. Instead, it means that 46 billion light-years is as far as light has had time to travel, given both the age of the cosmos and the rate of expansion. It is like being in a fog. The fog is not a wall, yet it limits how far you can see. Step forward and new ground becomes visible, but the fog also moves with you. In the same way, as time passes, light from new regions will reach us, and our observable universe will grow. Yet at the same time, other regions slip permanently beyond our horizon, carried away faster than light can chase. This creates a paradox of vision. Our horizon is not fixed. It changes with time, shaped by expansion, and it forces us to confront a humbling truth. What we can see is not the whole universe. It may not even be a large fraction of it. Beyond the horizon, there may be endless galaxies, endless stars, and perhaps even endless wonders we will never know. This idea challenges the human mind, which evolved to deal with horizons of a different kind. For our ancestors, the horizon was a line on the landscape. Walk far enough, and you would reach new lands. The ocean horizon promised mystery, but also discovery. In the cosmos, however, the horizon is different. No matter how far we travel, the cosmic horizon remains, because it is not a place, but a law of physics. Yet even as this law limits us, it inspires us. It tells us that the universe is larger than we can imagine, larger than we can measure, and perhaps larger than we can ever know. Some cosmologists believe that the universe might be infinite, with no edge at all. Others suggest it is finite but unbounded, like the surface of a sphere finite in area, yet without a boundary. Imagine being an ant walking across the surface of the Earth. The Earth is finite in size, but you would never encounter an edge. You could walk forever without falling off. Our universe might be similar, finite in volume, yet without an edge. But even these metaphors only take us so far, because the moment we speak of an edge, we ask the question, what lies beyond it? Is there a greater reality outside our observable cosmos? Could there be other universes, other realms of space and time, perhaps governed by different laws of physics? Or is there only nothing, no space, no time, no existence? These are not easy questions. In fact, they may not even be questions our minds, shaped by evolution on one small planet, are equipped to answer. But still, we ask. And in asking, we expand not only our knowledge, but our imagination. To explore what lies beyond the edge of the universe, we must begin by understanding the cosmic horizon itself. It is not just a boundary of sight, it is a boundary of knowledge. And like every frontier humanity has ever faced, it calls us forward with both fear and wonder. So when we ask, what is beyond the edge of the universe, we are really asking, what are the limits of reality? And what lies beyond the limits of human thought? This question does not just belong to astronomers or physicists. It belongs to all of us, for it is tied to the oldest human instincts, the longing to explore, to discover, and to know what lies beyond the next horizon. And thus, our journey begins, not at the edge itself, but at the understanding of what the edge truly means. When scientists speak of the observable universe, they are not talking about the universe in its entirety, but rather the portion that is accessible to us through light and other signals. This concept is one of the most important in modern cosmology, because it sets the boundary between what we can know and what forever lies beyond our reach. To truly appreciate what is meant by observable universe, we must dive into the mechanics of light, time, and cosmic expansion, and see how they work together to draw the circle of visibility that surrounds us. The observable universe is defined by a simple but profound fact. Light has a finite speed. In our everyday lives, the speed of light seems unimaginably fast. A beam of light can circle the Earth more than 7 times in a single second. But when we step into the scale of the cosmos, that very same speed becomes a limitation. Every photon that strikes our telescopes carries with it a history of travel. It tells us not just where an object is, but where it was when that light began its journey. This means that astronomy is the study of the past. When we look at the moon, we are not seeing it as it is right now, but as it was over 1 second ago. When we gaze at the sun, we are witnessing it as it was around 8 minutes earlier. If the sun were to vanish this instant, we would continue to see it shining in the sky for those 8 minutes before darkness revealed the truth. When our eyes wander to Proxima Centauri, the nearest star beyond the sun, the light entering our eyes departed that star more than 4 years earlier. And when astronomers point their instruments at the great Andromeda galaxy, the photons hitting their detectors set out over 2 million years ago, long before the first humans walked the Earth. And yet, those are only the nearest neighbors. Our deepest telescopes, like the James Webb Space Telescope, can peer far enough that the light has been traveling for billions of years. In those distant signals, we see galaxies as they were when the universe itself was young. We glimpse cosmic structures frozen in time, carrying with them stories from an era when matter first began to gather into the shapes we recognize today. But there is a limit to how far back this time machine vision can go. That limit is set by the age of the cosmos itself. The universe is thought to be about 13.5 billion years old. Light has only had that much time to travel. Therefore, the maximum distance from which light could have reached us is about 13.5 billion light years. But here lies a twist. The expansion of space stretches that distance much farther. Because the fabric of the cosmos has been expanding ever since the Big Bang, the actual radius of the observable universe is not 13.5 billion light years, but closer to 46 billion light years. How is this possible? Imagine you are walking along a moving walkway at an airport, but the walkway itself is stretching under your feet as you walk. Even if you walk steadily, the ground is expanding, and the distance you cover is far greater than your simple walking speed would suggest. Light traveling through an expanding universe faces a similar situation. The space between galaxies has grown while the light has been in transit. So the most distant galaxies we can observe are now far beyond 13.5 billion light years, carried outward by expansion to that larger distance of roughly 46 billion light-years. This radius of 46 billion light-years marks the current size of our observable universe. In volume, that is an incomprehensible sphere filled with hundreds of billions of galaxies, each containing hundreds of billions of stars, many of them surrounded by planets. Within this vastness lie black holes, clusters of galaxies bound together by gravity, and cosmic webs of dark matter weaving filaments that span millions of light years. All of it exists inside our observable sphere, like a bubble carved out of the larger unknown universe. But here is the crucial point. The observable universe is not the entire universe. It is simply the portion from which light has had time to reach us since the beginning of cosmic time. Beyond this horizon, there almost certainly lies more universe, perhaps infinitely more. Galaxies beyond our sight do not vanish. They are simply hidden by the barrier of time and expansion. They exist, but we will never see them. This raises an important question. If so much lies beyond what we can observe, why do scientists focus so much on the observable universe? The answer is that it defines the boundaries of empirical science. We can theorize about what lies beyond, but we cannot measure it directly. The observable universe is the canvas upon which all of our data is painted. It is the part of reality where evidence, not just speculation, can be gathered. And within that canvas lies one of the most profound features, the cosmic microwave background. This faint radiation, discovered in the 1960s, is the oldest light we can see. It comes from a time about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and photons to travel freely. Before that moment, the cosmos was opaque, filled with a fog of charged particles, scattering light in all directions. When that fog cleared, light burst forth, filling the universe with a glow that still lingers today as a faint microwave signal. This light forms a kind of wall in the sky, the farthest boundary of vision. When we look at the cosmic microwave background, we are staring as far back in time as possible to the very edge of our observable universe. Beyond that wall lies the unseeable. We know it must exist, for the same physics that shaped the regions we can observe must also have shaped regions beyond our reach. Yet we cannot observe them. And here, the definition of the observable universe becomes both scientific and philosophical. Scientifically, it is a region defined by the finite speed of light and the finite age of the cosmos. Philosophically, it is a reminder of the limits of human knowledge, that no matter how far our instruments reach, there will always be more beyond. But the story does not end there, because the observable universe itself is not fixed. As time passes, light from more distant regions will reach us, expanding our horizon. In the far future, if cosmic expansion were not accelerating, we would eventually see more of the universe as light from once hidden galaxies finally arrived. However, dark energy, the mysterious force driving the acceleration of expansion, ensures that this will not happen indefinitely. Instead, galaxies are rushing away faster and faster. Some that we can see today will fade into invisibility, slipping forever beyond our cosmic horizon. The observable universe will, in fact, shrink in terms of what remains visible to future observers. This dynamic boundary complicates the definition of the observable universe. It is not just a snapshot in space, but a process in time. It grows as light from new regions arrives, and it shrinks as galaxies vanish over the horizon. It is a breathing edge, shifting as the cosmos itself evolves. To visualize this, imagine standing on the shore of an infinite ocean. You see waves stretching out to the horizon, but you know the ocean continues far beyond what your eyes can reach. If the horizon itself moved with the tides, sometimes revealing new ships and sometimes hiding them, you would experience something similar to our changing cosmic horizon. The observable universe is our shifting shoreline, a temporary and ever-changing boundary drawn not by geography but by physics. Understanding this definition has profound consequences. It means that the universe is not limited to what we see. The observable universe is vast, but it is only a fraction of the whole. Beyond it may lie endless galaxies, or perhaps even different physical realities. But within it lies everything we can study, everything we can measure, everything we can test with science. And so, when scientists define the observable universe, they are not simply describing a size or a distance. They are defining the scope of knowledge itself. They are mapping the boundary between the known and the unknowable. It is this boundary that gives rise to some of the deepest questions. If the observable universe is so immense, what lies outside it? If we are confined to this bubble, are we forever blind to the true shape of reality? Or might there be ways, through mathematics or indirect evidence, to peer beyond? The observable universe is therefore not just a physical region, it is also a philosophical concept, a reminder that our place in the cosmos is both grand and humble. Grand because we can measure so much of it, and humble because we know there is far more we will never reach. This definition of the observable universe sets the stage for all the later questions we will explore. It is the circle of light within which we live and think. Outside that circle lies the ultimate mystery. When we speak about the farthest thing we can possibly see in the universe, we are not talking about a distant galaxy or a remote cluster of stars. We are talking about a wall of light that surrounds us in every direction. The oldest light that exists, a faint glow left behind from the birth of the cosmos itself. This light is called the cosmic microwave background, or CMB, and it is perhaps the most important discovery in modern cosmology. It is the ultimate edge of our vision, the farthest frontier of sight. To understand the cosmic microwave background, we must journey back almost to the very beginning. The universe began with the Big Bang around 13.5 billion years ago. In the earliest moments, the cosmos was unimaginably hot and dense, filled with energy and particles colliding with incredible violence. In that farthest state, matter could not exist in the form we know it today. Instead, the universe was a soup of fundamental particles, protons, electrons, and photons, mixed together in a seething plasma. In that plasma, photons, the particles of light, could not travel freely. Every time a photon tried to move, it would collide almost immediately with an electron, scattering off in a new direction. The universe at that stage was like the interior of a star, where light is trapped, endlessly bouncing around. This meant that the cosmos was opaque. No light could move freely for any significant distance. So the early universe was hidden in a blinding fog. This state continued for hundreds of thousands of years. But as the universe expanded, it also cooled. Eventually, around 380,000 years after the Big Bang, the temperature fell low enough for protons and electrons to combine into neutral hydrogen atoms. This moment is called recombination. With electrons bound into atoms, photons were no longer constantly scattered. Suddenly, the universe became transparent. Light was free to stream across space for the first time. Those first photons that escaped into the open cosmos are still traveling today. They have been moving for billions upon billions of years, stretching along with the expansion of space. Originally, this light would have been brilliant and white-hot, glowing in the visible spectrum. But as the universe expanded, the wavelengths of that ancient light were stretched longer and longer, a process known as redshift. What was once searing visible light is now stretched into the microwave region of the spectrum. That is why we call it the cosmic microwave background. This faint radiation fills the entire sky. No matter where you point a radio telescope, you will detect it. It is not tied to any particular galaxy or star. It comes from all directions, because it is the leftover glow of the entire young universe. In fact, when old television sets picked up static, a small percentage of that noise was caused by the cosmic microwave background. Every time someone tuned their television and saw the snowy fuzz of interference, they were, unknowingly, looking at the afterglow of creation itself. The discovery of this radiation happened almost by accident. In the early 1960s, two engineers, Arno Penzias and Robert Wilson, were testing a sensitive microwave antenna in New Jersey. They were trying to eliminate all sources of interference. But no matter what they did, they kept picking up a persistent background hiss. They even went so far as to clean out the antenna of nesting pigeons, convinced that the noise was caused by droppings. But the hiss remained. Eventually, they realized that what they had found was not interference at all, but the faint echo of the early universe. At the same time, theorists had already predicted such a glow should exist if the Big Bang theory were correct. The match was undeniable. Penzias and Wilson had discovered the cosmic microwave background, and with it had confirmed the Big Bang model of the universe. What makes this discovery so powerful is that the cosmic microwave background is a snapshot of the universe in its infancy. It is like a baby picture of the cosmos, frozen in time from when it was only a few 100,000 years old. By studying the CMB, scientists can learn what conditions were like in that primordial era, when the first atoms formed and matter began to settle into the structures that would one day become galaxies. The CMB is not perfectly smooth. It contains tiny fluctuations in temperature and density, slight variations of only a few parts in 100,000. These small ripples are incredibly important. They are the seeds of cosmic structure. Over billions of years, gravity amplified these small differences, drawing matter together to form stars, galaxies, and clusters. Without those initial ripples imprinted in the cosmic microwave background, the universe today would be uniform, a featureless sea of particles. Instead, those tiny fluctuations led to the rich and complex cosmos we inhabit. Modern satellites, like the Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probe, and the Planck satellite have mapped the CMB in extraordinary detail. What they reveal is a faint mottled pattern across the sky, like the texture of ancient parchment. These patterns are a cosmic fingerprint, encoding information about the universe's age, composition, and geometry. From them, scientists have measured the proportions of ordinary matter, dark matter, and dark energy. they have confirmed that space is flat on large scales. They have even tested models of cosmic inflation, the rapid expansion that occurred in the earliest fraction of a second after the Big Bang. In this way, the cosmic microwave background is more than just the farthest light we can see. It is a cosmic blueprint, a key that unlocks the story of how everything came to be. When we look at it, we are seeing the first moment the universe revealed itself, the moment when light became possible, the moment when transparency replaced opacity. But beyond the CMB, our vision fails. Before recombination, the cosmos was opaque and photons could not escape. No light exists from earlier times that can reach us directly. This is why the CMB is the farthest light. It is the final wall of sight, the cosmic horizon of photons. If we want to look back further than that, we must turn to other methods: gravitational waves, neutrinos, or theoretical physics, but not to light. The CMB also tells us something humbling, that the universe, though vast and majestic, has limits to what can be observed. The light from before recombination will never reach us. The events of the very first moments, the birth of inflation, the spark of creation, these remain forever hidden from direct vision. What we see is a curtain, a final glow that marks the boundary of sight. Philosophically, this is staggering. Humans have always pushed horizons. We crossed mountains, oceans, and even space to the moon and beyond. Yet here is a horizon we cannot cross with our eyes. No matter how powerful our telescopes, the CMB is the final image in light. And yet, instead of discouraging us, it deepens the mystery, for within those faint microwaves lies a story still unfolding. As technology improves, we will continue to refine our maps of the CMB. We will search for the subtle polarization patterns that could confirm cosmic inflation. We will use it to test the very structure of physics itself. In this sense, the CMB is both an ending and a beginning. It is the end of vision, but the beginning of understanding. So when we ask what lies at the farthest edge of the universe we can see, the answer is simple and profound. A glow, faint and ancient, stretched across the sky, whispering to us from nearly 14 billion years ago. This glow is not a galaxy, not a star, not a planet. It is light itself, freed for the first time from the fog of creation. It is the oldest story written in the language of photons. The cosmic microwave background is therefore not just radiation. It is a time capsule, a cosmic fossil, the earliest relic of our universe's memory. It reminds us that we live inside a story far larger than ourselves, a story whose opening chapters are written in a language we are only beginning to translate, and beyond that glowing wall, darkness, silence, mystery. When we talk about the universe, one of the most natural questions people ask is whether it has an edge. In ordinary life, everything we encounter has some kind of boundary. A house has walls, a city has borders, an island has a shoreline. It feels intuitive to think of the universe in the same way, as if there must be some cosmic wall or end point where space simply stops. Yet in modern cosmology, the idea of an edge becomes far more complex and perhaps even misleading. To begin, let us remember that the observable universe already gives us one kind of edge, a horizon created by the finite speed of light and the finite age of the cosmos. Beyond that horizon lies more universe, but we cannot see it. This is a limit of observation, not necessarily a limit of reality. The edge of the observable universe is not like the edge of a table or a cliff. It is more like the edge of sight in a fog. The fog is not a physical object, but it blocks your vision. If you move forward, the fog also shifts, and you still cannot see beyond it. The cosmic horizon works in the same way. But what about a physical edge? Does space itself end somewhere, like the last page of a book? Here, we step into a world of possibilities, some rooted in physics, others still speculative. First, we must explore the concept of space as a geometric structure. Einstein's general theory of relativity tells us that space and time are not rigid backdrops, but flexible fabrics that can bend and curve. Gravity is not a force acting across emptiness, but the warping of this fabric. If space can curve, then the universe may not be infinite, but finite and unbounded. Consider the surface of the Earth. The Earth's surface is finite. You can measure its area, but it has no edge. If you start walking in one direction, you will never encounter a wall. You can circle the globe indefinitely. The Earth's surface is an example of a finite but unbounded geometry. Some cosmologists propose that our universe might be similar, except in 3 spatial dimensions rather than 2. In such a case, the universe would have a measurable volume, yet you would never reach an edge, no matter how far you traveled. But could the universe truly end with a hard boundary? What would that even mean? Imagine flying a spaceship straight ahead at impossible speeds. Would you eventually reach a cosmic wall like glass, preventing you from going further? Most physicists argue that this does not make sense. Space is not like a room with walls. It is the very fabric in which things exist. To speak of the end of space is to ask about the absence of geometry itself. It would be like asking what lies north of the North Pole. The concept ceases to apply. Yet human intuition struggles with this. Our minds evolved to deal with finite objects and landscapes, not with infinite or unbounded geometries. So the question of an edge keeps returning. It is not foolish to ask, it is deeply human. Now let us turn to the possibility of an infinite universe. In this scenario, space goes on without limit in every direction. There is no edge because there is no boundary. Just as numbers stretch without end on a number line, galaxies could stretch endlessly across space. In such a cosmos, the observable universe is just a tiny patch, like a circle of light cast by a lantern in the night. Outside that circle, the night continues forever. The infinite universe raises astonishing implications. In an infinite expanse, patterns eventually repeat. With enough galaxies and enough stars, there would eventually be regions almost identical to our own. Some theorists suggest that somewhere, unimaginably far away, there may be another patch of universe with a solar system nearly identical to ours, perhaps even with another Earth and another version of you. This is not science fiction, it is mathematics. Infinity allows for every possibility to occur, somewhere, sometime. But there are other scenarios. What if the universe is not infinite, but finite, with some kind of exotic topology? Imagine walking through a video game world, where the screen wraps around, go far enough to the right, and you reappear on the left. In mathematics, this is called a torus, or donut shape. Some models of the universe suggest that space could be finite, yet connected in such a way that if you traveled long enough in a straight line, you might eventually return to your starting point just as a ship circling the globe returns home. If true, this would mean the cosmos has no edge, but it also is not infinite. It would be vast, yet self-contained. Of course, we cannot ignore the possibility that our understanding is incomplete. Perhaps space does have a boundary, but not in a way we can easily imagine. Could there be a transition zone where our universe gives way to something else? Another region of space with different physical laws? Some theories of the multiverse propose just this. In these models, our universe is like a bubble, floating in a cosmic foam, surrounded by other bubbles. The edge of our universe would then be the boundary of our bubble, where it meets the energy of the greater multiverse. But here lies the difficulty. If such an edge exists, we may never be able to see or touch it. The expansion of space keeps pushing everything beyond our observable horizon. Any true boundary of the cosmos would almost certainly lie far outside what light can ever reach. So, while it is possible that our universe has an edge in this multiversal sense, it is not an edge we could ever encounter directly. Philosophically, the absence of an edge may be just as profound as the presence of one. If the universe is infinite, then our place within it shrinks even further. The observable universe, already incomprehensibly large, becomes a speck in an endless ocean. And if the universe is finite but unbounded, then we must accept a geometry that defies our everyday intuition. A cosmos without walls, yet with a definite size. The search for an edge also forces us to confront the meaning of nothing. If the universe had a boundary, what would lie beyond it? Would there be empty space? But space itself is part of the universe. Would there be time? But time, too, is part of the cosmos. Perhaps beyond the universe lies true nothingness, a state without space, without time, without laws. But how can we even speak of beyond if space does not exist there? This is the paradox. The very language we use breaks down at the edge of thought. And yet, even without direct answers, the question of an edge drives scientific discovery. It pushes physicists to test models of geometry, to measure the curvature of space, to analyze the cosmic microwave background for hints of topology. So far, the evidence suggests that on the larger scales, the universe is remarkably flat. This could mean it is infinite, or it could mean it is finite, but so vast that any curvature is undetectable within our observable patch. Either way, the conclusion is the same. We do not see an edge. We see a cosmos that stretches far beyond what we can observe, perhaps endlessly. The only true edge we know is the horizon of observation, drawn by light and time. Beyond that, whether space continues forever, loops back on itself, or gives way to other realms, remains a mystery. In the end, asking if there is an actual edge may reveal more about ourselves than about the universe. It shows how deeply we long for boundaries, for something to grasp, for a place where we can say, here is the end. But the cosmos resists such simplicity. It is vaster, stranger, and more elusive than our metaphors allow. And perhaps that is the greatest lesson. The universe may not have an edge at all. Instead, it has horizons shifting, expanding, receding horizons that define not the limits of reality, but the limits of what we can know. The idea that the universe is expanding is one of the most transformative discoveries in human history. Before the 20th century, many scientists believed the cosmos was eternal and unchanging, a fixed stage on which stars and galaxies drifted like actors. The night sky appeared steady and permanent, its constellations familiar across centuries. But hidden within that seeming stillness was a secret so profound that once revealed, it reshaped our entire understanding of existence. Space itself is stretching, and the galaxies are carried along like leaves floating on an ever-widening river. To understand this expansion, we must first speak about light. For light is the messenger that carries news of the cosmos to us. When an object emits light, the wavelength of that light encodes information about its motion. This is the principle of redshift and blueshift, effects first studied in sound and later applied to the universe itself. Consider the sound of a train whistle as it approaches and then passes. As the train comes toward you, the pitch is higher. As it moves away, the pitch lowers. This change happens because the motion of the train compresses or stretches the sound waves. When waves are compressed, their frequency increases. When they are stretched, the frequency decreases. Still, the balloon captures enough truth to be profoundly useful. It gives us a way to visualize how galaxies recede, how distances stretch, and how the universe can be finite yet unbounded. Now consider what happens as the balloon inflates more and more. The dots move farther and farther apart. If the inflation continues long enough, the dots on the far side of the balloon will recede so quickly that the ant's vision cannot keep up. This mirrors our cosmic horizon, the limit beyond which galaxies recede faster than light due to the stretching of space. Once again, the analogy reflects a key feature of reality. That expansion creates horizons, regions forever out of reach. Philosophically, the balloon analogy also helps us think about the possibility of curvature. A perfectly flat balloon does not exist, it always curves. Our universe, according to current measurements, appears nearly flat on the largest scales. But it could be that it has a slight curvature, either positive like a sphere or negative like a saddle. If the universe has positive curvature, it might be finite but without edges, like the balloon's surface. If negative, it might stretch infinitely, but in a way that is still curved. The analogy also raises questions about the beginning. When you look at a balloon, you see it inflating from a smaller size. Naturally, you ask, what did it look like before? Was it completely deflated? Did it begin as a tiny speck? In the same way, when we hear the universe is expanding, we ask, what was it expanding from? The balloon tempts us to imagine a center, a place from which the expansion began. But in cosmology, there is no center. The Big Bang did not happen at one point in space. It happened everywhere simultaneously. The balloon helps here too. No dot on its surface is special. The inflation occurs everywhere at once. Yet, the balloon has its limits. The surface is two-dimensional, but the universe is three-dimensional. Perhaps more, if extra dimensions exist, as some theories suggest. Also, balloons have edges in the higher dimension of their volume, while the universe may not have any outside at all. Still, as long as we remember its limitations, the balloon analogy remains one of the clearest tools we have for describing expansion. Another useful twist is to imagine not just blowing up the balloon, but marking smaller patterns on it, clusters of dots connected by short lines. As the balloon expands, the distances between clusters grow, but the clusters themselves remain intact. This mirrors the way galaxies within clusters are held together by gravity, even as the universe expands overall. Expansion affects the large-scale structure of space, but local regions bound by gravity or other forces resist it. This is why our solar system, our galaxy, and even our local group of galaxies do not expand with the universe. The balloon shows us that expansion dominates on the largest scales, but gravity dominates locally. There is also something deeply poetic about the balloon analogy. To imagine our entire cosmos as the surface of a balloon inflating into mystery is to capture the sense of wonder that cosmology inspires. It is both playful and profound. It takes a child's toy and transforms it into a model of the universe, showing that sometimes the deepest truths can be explained through the simplest images. But perhaps the most important lesson the balloon teaches is humility. We are one tiny dot on the surface, surrounded by countless others, all carried along by forces far beyond our control. The expansion of space is not something we can stop or alter. It is a feature of reality itself, written into the laws of physics. The balloon reminds us that we are passengers in a vast journey, our fate tied to the expansion of the cosmos. And as the balloon continues to stretch, we are faced with profound questions. Will it expand forever, growing thinner and emptier with time? Will it one day stop, perhaps collapsing back inward like a balloon deflating? Or will it reach a state of balance, hovering between endless growth and ultimate collapse? These are not just abstract puzzles. They are questions about the destiny of everything we know. So when we use the balloon analogy, we are not just teaching a scientific idea. We are inviting ourselves to imagine the universe in new ways. We are challenging our limited intuition, stretching our minds just as space itself stretches. And in doing so, we come a little closer to understanding the mystery of the cosmos. The balloon is not the universe, but it is a window. Through it, we glimpse how expansion works, why there is no center, why there may be no edge, and how horizons form. It is a reminder that sometimes the greatest truths can be explained with the simplest tools. And in the faint stretching of that imagined balloon, we hear an echo of reality. The universe itself endlessly expanding, carrying us along into the unknown. For centuries, human beings have wondered whether our universe is the only one. The word universe itself once implied everything that exists, the totality of reality. But as science has advanced, new ideas have emerged that challenge this assumption. Perhaps our universe, vast and incomprehensible though it is, might be only one bubble in a far greater sea. This possibility is known as the multiverse hypothesis. The multiverse is not a single theory, but a family of ideas, born from different areas of physics and cosmology. Each version suggests that what we call the universe may be just one of many, and that beyond the edge of our observable cosmos, there could be other realms, perhaps infinite in number, each with its own properties, its own history, maybe even its own laws of nature. To understand why scientists take this idea seriously, we must trace it back to its roots. One of those roots lies in the theory of cosmic inflation. In the early 1980s, physicist Alan Guth proposed that in the first fraction of a second after the Big Bang, the universe underwent a period of exponential expansion. During this inflationary phase, space expanded faster than the speed of light, smoothing out the cosmos and explaining why it appears so uniform in every direction. Inflation also explains the distribution of tiny fluctuations we see imprinted in the cosmic microwave background. But inflation may not be a one-time event. According to some models, it could be eternal. In this view, inflation ends in certain regions, creating bubble universes where normal cosmic evolution begins. Our universe would be one such bubble. But in other regions, inflation continues, endlessly spawning new bubbles. The result is an infinite multiverse, a cosmic foam of universes stretching without end. Each bubble might have different physical constants, different strengths of gravity, different particle masses. Some might allow stars and galaxies to form, others might collapse almost instantly, and still others might be radically alien, with physics we could barely imagine. Another root of the multiverse idea comes from string theory, a framework that attempts to unify all the fundamental forces of nature. String theory suggests that reality may have more than the familiar 3 dimensions of space and 1 of time. There could be 10 or even 11 dimensions, most of them curled up so tightly that we cannot perceive them. In this higher dimensional landscape, many different possible universes could exist, each corresponding to a different configuration of these hidden dimensions. Some physicists speak of a string landscape, a vast collection of possible universes, of which ours is just one. Then there is the many worlds interpretation of quantum mechanics. In the quantum world, particles do not exist in definite states until they are observed. Instead, they exist in superpositions, combinations of possibilities. When a measurement is made, the wave of possibilities collapses into a single outcome. But the many worlds interpretation proposes something more radical, that all possible outcomes actually occur, each in its own branching universe. Every quantum event creates a new universe, splitting reality into countless parallel histories. In this view, there is a universe where you decided to take a different path this morning, another where you never existed at all, and still another where history unfolded in ways utterly unlike our own. These different versions of the multiverse hypothesis, cosmic inflation, string landscapes, quantum, many worlds, all suggest that our universe may not be unique, but they differ in scope and character. Some speak of vast cosmic bubbles separated by inflating space. Others describe parallel universes stacked in higher dimensions. Others imagine branching timelines splitting off from every event. Each paints a picture of reality far larger and stranger than the one we know. But what would it mean if the multiverse is real? For one thing, it would help answer a puzzling question. Why does our universe appear so finely tuned for life? The laws of physics as we know them are balanced on a razor's edge. If the strength of gravity was slightly different, stars might never have formed. If the ratio of matter to antimatter had been slightly altered, the universe might be empty. If the energy of the vacuum were a little higher, space might have blown apart too quickly for galaxies to coalesce. The odds of these constants aligning in just the right way seem astronomically small. In a multiverse, this fine-tuning is no mystery. If countless universes exist, each with different laws, then most will be sterile. But some, by chance, will have the right conditions for complexity and life. We happen to live in one of those, because only in such a universe could beings like us exist to ask the question. This is called the anthropic principle. It is not a satisfying explanation to everyone, but it does make sense. In a vast multiverse, the improbable becomes inevitable. However, the multiverse hypothesis is controversial. Critics argue that it is unscientific because other universes, if they exist, may be forever beyond our ability to observe. Science relies on testable predictions, and if we cannot detect or interact with other universes, how can we ever prove their existence? Defenders reply that indirect evidence may still be possible. For instance, if our universe is a bubble, it might occasionally collide with another bubble, leaving scars in the cosmic microwave background. Or, if string theory is correct, the pattern of particles and forces we see might reflect deeper structures in a higher dimensional reality. The debate is ongoing, and perhaps it always will be. But even if the multiverse remains unprovable, it forces us to confront the limits of our imagination. The idea that our universe could be one of countless others expands our sense of scale beyond comprehension. It humbles us, reminding us that what we call everything may be only a fraction of reality. Philosophically, the multiverse raises profound questions. If infinite universes exist, does that mean infinite versions of ourselves exist too? Are there universes where civilizations far older and wiser than ours have flourished, or universes where nothing ever formed at all? Does each decision we make create a new branch of reality? And if so, what does that mean for the idea of free will? These are not just scientific puzzles, but existential ones. And yet, there is something strangely comforting in the multiverse. If reality is truly infinite, then nothing is ever wholly lost. Every possibility is realized somewhere. Every dream, every path not taken, every version of existence exists in some universe. Our cosmos is vast enough to contain all stories, all outcomes, all worlds. So when we ask what lies beyond the edge of the universe, one answer is this: more universes, a multiverse, endless and eternal, bubbling and branching beyond our horizon. We may never see it directly, but the very possibility expands our sense of wonder. It tells us that the edge of our universe may not be the edge of reality at all, but merely the boundary of our small cosmic bubble. And in that greater sea of universes, we are a single wave, fleeting yet part of an infinite ocean. To understand the true strangeness of what may lie beyond the edge of our universe, we must travel back to the very first fraction of a second after the Big Bang, to a time so early and so extreme that even our best theories struggle to describe it. In this primeval instant, the cosmos was governed not by the smooth fabric of space and time we know today, but by a restless and seething reality, sometimes called quantum foam. Out of this strange foundation emerged one of the most powerful ideas in modern cosmology: inflation, the theory that our universe expanded at an unimaginable rate in its earliest moments. Let us begin with quantum foam. According to the principles of quantum mechanics, the smallest scales of reality are never calm. Particles flicker in and out of existence. Energy surges and vanishes. Space itself trembles with uncertainty. This is the quantum vacuum, a place where nothing is ever truly still. When magnified to the scales of the earliest universe, this restless activity becomes overwhelming. Physicist John Wheeler described it as a foam, a bubbling and boiling foundation where space and time fluctuate wildly. At this scale, The smooth laws of general relativity break down. Space is no longer continuous but fractured, torn by constant fluctuations. In one instant, the geometry might bend one way. In the next, it might bend another. The concept of distance, direction, even causality becomes blurry. This is the landscape from which our universe emerged. A seething sea of possibilities with no fixed shape. And then, something extraordinary happened. According to the inflationary theory first proposed by Alan Guth in the early 1980s, a peculiar form of energy called the inflaton field drove an era of exponential expansion. In less than a trillionth of a trillionth of a trillionth of a second, the universe ballooned from subatomic scales to cosmic scales, smoothing itself out in the process. Inflation solves several puzzles that had long troubled cosmologists. One puzzle is the horizon problem. The universe looks remarkably uniform in every direction. The cosmic microwave background shows nearly the same temperature no matter where we look. But regions on opposite sides of the sky are so far apart that under ordinary expansion, they could never have been in contact. How could they have the same temperature if they never exchanged information? Inflation solves this by suggesting that before expansion, those regions were once close enough to interact. Inflation then stretched them apart, carrying their uniformity across the cosmos. Another puzzle is the flatness problem. Measurements show that the geometry of space is nearly perfectly flat, not curved like a sphere or saddle. But maintaining this flatness over billions of years is unlikely without fine-tuning. Inflation explains it naturally. Rapid expansion would have smoothed out any curvature, leaving the cosmos nearly flat. Inflation also accounts for the seeds of cosmic structure during the inflationary phase. Tiny quantum fluctuations, minute variations in density were stretched to cosmic scales. These fluctuations later grew under gravity to form galaxies, clusters, and the vast web of matter we observe today. In other words, the structure of the universe is a magnified imprint of quantum noise, fossilized by inflation. But inflation may not have been a one-time event. Many models suggest that inflation is eternal. In this picture, inflation never ends everywhere at once. Instead, it stops in patches, creating bubble universes where normal cosmic evolution begins. Our universe would be one such bubble. And meanwhile, inflation continues elsewhere, spawning more and more bubbles endlessly. This leads to the multiverse concept described earlier, an infinite sea of universes, each born from the inflating foam. At the heart of this lies the quantum foam itself. Because of quantum uncertainty, the vacuum is never empty. Fluctuations constantly create pairs of particles and antiparticles that annihilate almost instantly. Occasionally, such fluctuations can trigger inflation in a local region, giving birth to a new universe. In this sense, universes might be bubbling into existence all the time, each emerging from the foam of quantum reality. This vision is mind-bending. It means that our entire cosmos, with its billions of galaxies and trillions of stars, may have sprung from a tiny quantum fluctuation, a random tremor in the fabric of nothingness. And it means that countless other universes may exist beyond ours, each with its own properties, each born from the same chaotic sea. But quantum foam and inflation also raise deep questions. What exactly is the inflaton field? We do not know. It is a hypothetical energy that fits the equations but has never been directly observed. What caused inflation to start, and why did it end in our region? Again, we do not know. Inflation explains much, but it also leaves mysteries. Philosophically, these ideas challenge our notions of beginning and end. If universes can arise spontaneously from quantum foam, does that mean creation has no ultimate origin? Is reality itself eternal, forever bubbling with new cosmoses? Or is there some deeper law that governs even the foam, something beyond our current theories? Inflation also raises the possibility of other universes with different physical laws. If the parameters of the inflaton field vary, then each bubble universe could have different constants, different strengths of gravity, different charges of particles, different behaviors of matter and energy. Some universes might allow stars and life to form. Others might collapse instantly or expand into emptiness. In this way, quantum foam and inflation connect directly to the question of what lies beyond the edge of our universe. Beyond our horizon may lie other bubbles, invisible to us, born from the same foam. Perhaps some are colliding with ours even now, leaving faint imprints in the cosmic microwave background. Perhaps others are forever unreachable, separated by inflating space that grows faster than light can cross. The image is staggering. Reality as a vast ocean of foam, each bubble a universe, each expanding into its own history. Our cosmos, immense as it seems, becomes just one froth in an endless sea. And yet, despite its strangeness, this picture arises naturally from the mathematics of quantum physics and relativity. It is not wild speculation, but the logical extension of theories tested in many ways. Whether it is ultimately correct remains unknown, but it is a framework that unites the smallest scales of quantum foam with the largest scales of cosmic expansion. So, when we look at the universe and ask what lies beyond its edge, one answer is this: quantum foam and eternal inflation. A restless foundation bubbling with possibilities, from which universes spring like sparks from a fire. And within one of those sparks, we find ourselves wondering at the immensity of it all. When we speak of horizons, we usually think of the line where the Earth meets the sky, a boundary that recedes as we move toward it. But in cosmology, the horizon has a far deeper meaning. It is not just a line of sight, but the ultimate limit of what we can ever observe. Our cosmic horizon is defined by the age of the universe and the expansion of space. Beyond it, there are regions whose light has not had time to reach us, and in many cases, regions whose light will never reach us at all. This raises a haunting and profound question. What lies beyond our horizon now? To answer this, we must recall the nature of the observable universe. Light has been traveling for around 13.5 billion years since the Big Bang. But because space itself has been expanding, the radius of the observable universe is about 46 billion light-years. Everything within this immense sphere is visible to us in principle, though often only as faint smudges of ancient light. Everything beyond it lies hidden, beyond the reach of photons. But just because we cannot see beyond the horizon does not mean there is nothing there. In fact, all evidence suggests the opposite. The laws of physics do not stop at our horizon. The same processes that formed galaxies and stars here must also have occurred there. So beyond our horizon now, in every direction, There are galaxies upon galaxies, clusters upon clusters, stretching into the unseen. Imagine standing on the shore of a vast ocean at night. The water extends beyond the curve of the earth, but you cannot see it. You know it is there because the laws of geography do not change, just because your eyes cannot reach that far. The same is true of the universe. The cosmos does not suddenly end at 46 billion light-years. It continues, following the same laws, likely filled with more of the same structures we observe nearby. What might those hidden regions look like? Based on what we see in our observable patch, we can make informed guesses. There will be galaxies, many of them spiral like our Milky Way, others elliptical or irregular. There will be stars forming and dying, black holes consuming matter, planets orbiting suns. There will be nebulae glowing with ionized gas, clusters bound together by gravity, and superclusters forming the great cosmic web. Beyond our horizon now lies a mirror of what we see here, an extension of the same grand structures. But expansion complicates the picture. Because space stretches faster at greater distances, many of these galaxies are receding from us faster than the speed of light. This does not violate relativity, because it is space itself that is expanding, but it means their light will never reach us. In fact, many of the galaxies we see today are already beyond the point of no return. We see them as they were billions of years ago, but their present selves are forever lost to us. They are like ships that have sailed over the horizon, visible in memory, but gone in reality. And then there is the tantalizing possibility of other universes altogether. If inflation is eternal, then beyond our horizon there may not just be more of our universe, but entirely separate bubbles, each with different laws. Collisions between such bubbles, if they occurred, might leave faint imprints in the cosmic microwave background, subtle scars on the sky that could be our only evidence of realities beyond. For now, however, we cannot see those places. Beyond our horizon now lies an infinity of unknowns, a realm where imagination must step in, where observation cannot go. Some philosophers argue that this makes the question meaningless. If we can never see beyond the horizon, why speculate? But history shows that speculation often guides discovery. Once, people speculated about lands beyond the ocean, and eventually ships found them. Once, people speculated about planets beyond Saturn, and telescopes discovered them. Though the cosmic horizon is more absolute, the act of imagining what lies beyond still drives our science forward. It shapes our theories, guides our models, and keeps our curiosity alive. In the end, what lies beyond our horizon now is both simple and profound. There are more galaxies, more stars, more worlds, real, tangible places we will never reach. And there may also be the beginnings of other universes, strange realms with different rules, forever separated from ours. The horizon hides them, but it does not erase them. To live in such a universe is to accept both wonder and limitation. Wonder because the cosmos is richer than we can ever grasp. Limitation because we will never grasp it all. But perhaps that is the point. The horizon reminds us that mystery is built into the fabric of reality, and sometimes the greatest truths are not the ones we see, but the ones we know must exist just beyond our sight. Perhaps the most difficult idea to confront when asking what lies beyond the edge of the universe is the concept of nothing. Our everyday experience offers us no true encounter with nothingness. Even an empty room has air molecules, light bouncing from the walls, sounds echoing faintly. Even outer space, which seems like emptiness, is filled with particles, fields, and radiation. So, when scientists or philosophers speak of nothing, we must pause and ask, what do they mean? For most of human history, nothing was imagined as an absence in ancient philosophy. Nothing was the void, a blank emptiness that existed between atoms. For others, nothing was the realm before creation, the darkness from which the world emerged. But modern physics complicates this picture. In physics, nothing is not simple emptiness. The vacuum of space is alive with energy, a restless sea of fluctuations known as the quantum vacuum. Even empty space teems with particles popping in and out of existence, fields vibrating, and virtual energy shaping reality. So if this is nothing, it is a very busy nothing. Quantum mechanics teaches us that absolute emptiness may not exist. The uncertainty principle ensures that fields can never be completely still. There is always a jitter, a fluctuation. From this activity, particles can emerge, forces can act, and even entire universes might be born. This challenges our intuitive notion of nothing. When we ask what lies beyond the universe, one possible answer is nothing. But this nothing is not a simple blankness. It might be a quantum foam, a restless potential from which universes arise. In this sense, nothing is not the absence of reality, but the possibility of all realities. Some scientists suggest that the Big Bang itself could have emerged from such nothing. If the vacuum is unstable, then a fluctuation could spark the creation of space and time. One moment, there is nothing, no space, no time, no matter, and the next, there is everything. This idea is profoundly unsettling, for it erases the need for a cause in the traditional sense. Creation may not require a creator, but may arise naturally from the laws of quantum mechanics. But here we encounter a paradox. If the laws of physics exist to allow something to emerge from nothing, then can nothing ever truly exist? If nothing is defined as the absence of everything, then it cannot contain laws, rules, or potentials. Yet, if there were truly nothing, then no universe could arise. So perhaps the very idea of nothing is incoherent. Perhaps what we call nothing is always, in some way, something. This paradox has haunted philosophers for centuries. Why is there something rather than nothing? If nothing were the natural state, why does anything exist at all? Some argue that nothing is unstable, that existence is more likely than non-existence. Others argue that nothing is impossible, that some form of reality must always be. Cosmology adds another layer to this debate. If the universe is infinite, then the idea of nothing beyond its edge may never apply, because there is no edge. Space may stretch endlessly, always filled with galaxies, stars, and energy. In that case, the question of nothing beyond becomes meaningless. If the universe is finite, unbounded like the surface of a sphere, then again there is no edge and no beyond. But if the universe is a bubble in a multiverse, then perhaps beyond our bubble lies a kind of nothing, not an absolute void, but an inflating field, a quantum foam from which new universes are born. This nothing is creative, fertile, restless. It is not the end, but the beginning of all things. The human imagination struggles with these abstractions. When we try to picture nothing, we imagine blackness. But blackness is still something. It is darkness, the absence of light, but it is still a visual experience. True nothing would not be black or white or empty. It would not be space or time. It would not be describable at all, because description requires qualities, and nothing has none. Perhaps this is why many philosophers and scientists conclude that true nothing cannot exist. The very act of asking the question implies something, a mind to ask it, a framework in which to pose it, laws to govern it. Nothing, in the absolute sense, is beyond comprehension. And yet, the concept of nothing remains important, because it marks the boundary of our thought. When we ask what lies beyond the universe, and we answer nothing, we are really saying beyond the universe lies the limit of our imagination. There is also a profound beauty in this. Nothingness has always inspired human creativity. Poets have written of the void, mystics of the silence beyond being, scientists of the vacuum from which worlds emerge. In every field, nothing has been a canvas for possibility. It is the backdrop against which existence shines. And perhaps this is the ultimate lesson. Nothing may not exist as a real state, but as a concept. It forces us to confront the mystery of being. It reminds us that existence is not guaranteed, that reality could have been otherwise, that the fact there is something rather than nothing is itself the greatest wonder. So when we speak of what lies beyond the edge of the universe, and one answer is nothing, we must take care. We do not mean a simple void. We mean either the restless potential of quantum foam, the unseeable absence of space and time, or the limit of our own understanding. In all cases, nothing is not empty. It is full of meaning, paradox, and possibility. And so, the question remains, what lies beyond? Perhaps more universes, perhaps infinite space, perhaps a fertile quantum vacuum, or perhaps simply nothing, a nothing so absolute that it cannot even be thought. Whatever the answer, the concept of nothing stands as one of the deepest mysteries, the shadow against which all of existence is measured. When we look at the universe, we see three dimensions of space: length, width, and height, and one dimension of time. These four dimensions form the fabric of reality we inhabit, the stage on which every star, planet, and galaxy exists. But what if the cosmos is not limited to these familiar dimensions? What if, hidden beyond our senses, there are more layers to reality, higher dimensions that shape everything we know? And what if these higher dimensions harbor parallel universes, entire realms of existence stacked beside our own? This idea is not science fiction. It is born from real attempts to unify the laws of physics, to reconcile the small-scale world of quantum mechanics with the large-scale world of general relativity. One of the most ambitious frameworks for this unification is string theory. According to string theory, the fundamental building blocks of the universe are not point-like particles, but tiny vibrating strings of energy. The vibrations of these strings determine the properties of particles, their mass, their charge, the forces they experience. Philosophically, the idea of parallel universes and higher dimensions challenges our deepest assumptions. We like to think of our universe as unique, as everything that exists, but If higher dimensions harbor countless universes, then our cosmos is just one of many. The edge of our universe would not be the edge of reality, but merely the edge of our brain, our slice of higher dimensional space. This raises questions about connection. Could we ever travel between universes? Could higher dimensions provide shortcuts, wormholes that link one brain to another? In science fiction, such portals are common, but in real physics, they remain speculative. The energy required to access higher dimensions would be enormous, and the stability of such connections doubtful. Yet the mere possibility excites imagination. If parallel universes exist, then perhaps in some distant future, advanced civilizations might learn to reach them. And then there is the question of life. If other universes exist, do they harbor beings like us, or are they too alien for life to arise? If the laws of physics vary, many universes may be sterile, collapsing before galaxies form, or expanding too quickly for stars to ignite. But in a vast multiverse, some will inevitably have the right conditions. Life may not be rare, but inevitable, sprouting wherever the laws permit. Somewhere in higher dimensions, civilizations may thrive forever hidden from us. Critics of these ideas argue that parallel universes and higher dimensions are untestable and therefore unscientific. After all, if we cannot observe them, how can we claim they exist? Defenders reply that evidence may be indirect. For example, if gravity leaks into higher dimensions, we might detect its weakening at small scales. If brain collisions occurred, they might leave imprints in the cosmic microwave background. If string theory is correct, it could reveal its signatures in particle accelerators. Even if direct proof eludes us, the concepts remain valuable. They expand our thinking, push the boundaries of imagination, and remind us that reality may be far stranger than common sense suggests. So, what lies beyond the edge of our universe? One answer is this: parallel universes in higher dimensions. Unseen realms layered beside our own, each with its own laws, each as real as ours, but forever hidden. They are the shadows of reality, the unseen pages of the cosmic book. Whether we ever prove their existence or not, they remind us that the universe we see is not the whole of reality, and that beyond the horizon of our knowledge may lie entire worlds, entire histories, entire infinities waiting in higher dimensions. Among the many mysteries that surround the cosmos, few are as baffling and profound as dark energy. It is invisible, it is elusive, and yet it dominates the fate of the universe. More than 2 decades ago, astronomers discovered that the expansion of the universe is not slowing down as once believed. Instead, it is accelerating, driven by some unknown force that pushes galaxies apart with ever-increasing speed. This force, which we call dark energy, will determine what lies beyond the edge of the universe and how the cosmic story will unfold in the far future. To understand dark energy, we must begin with the discovery that revealed it. In the late 1990s, 2 independent teams of astronomers were studying distant Type 1, a supernovae. These stellar explosions are so bright and so consistent that they serve as cosmic yardsticks, allowing scientists to measure distances across billions of light years. By comparing the apparent brightness of these supernovae with their redshifts, astronomers can determine how fast the universe was expanding when the light was emitted. The expectation was that the universe's expansion should be slowing under the pull of gravity. After all, every galaxy attracts every other galaxy. The farther apart they are, the weaker the pull, but on cosmic scales, gravity should still gradually break the expansion. Yet the data showed the opposite. Distant supernovae were dimmer than expected, meaning they were farther away than they should have been if expansion were decelerating. The only explanation was that expansion had sped up. This discovery shocked the scientific community. It implied the existence of a force counteracting gravity on the largest scales, a force that pushes space itself to expand faster and faster. Cosmologists gave it a simple name: dark energy. But what is dark energy? We do not know. It might be a property of space itself, sometimes called the cosmological constant, first introduced by Einstein. In this view, even empty space has energy, a vacuum energy that remains constant as the universe grows. As more space comes into existence, more vacuum energy appears, driving expansion ever faster. Another possibility is that dark energy is a dynamic field, sometimes called quintessence, that changes over time. Unlike the cosmological constant, which is fixed, quintessence could evolve, growing stronger or weaker, perhaps even reversing its effect in the far future. Whatever its nature, dark energy dominates the universe. Current estimates suggest that about 70% of the total energy content of the cosmos is dark energy. About 25% is dark matter, which interacts through gravity but not light, and only about 5% is the ordinary matter that makes up stars, planets, and us. This means that everything we can see, every star in the night sky, is only a tiny fraction of reality. The true master of the cosmos is dark energy, and dark energy dictates the fate of expansion. If it remains constant, the universe will expand forever, faster and faster, leading to what is called the heat death of the cosmos. In this scenario, galaxies will drift apart until they vanish beyond each other's horizons. Stars will burn out, black holes will slowly evaporate, and the universe will fade into darkness and cold. But other possibilities exist. If dark energy grows stronger with time, expansion could accelerate so violently that it tears apart galaxies, stars, planets, and even atoms. This apocalyptic scenario is called the Big Rip. In the Big Rip, the very fabric of space stretches so quickly that no structure can survive. The cosmos ends not in fire or cold, but in a catastrophic unraveling. On the other hand, if dark energy weakens or changes sign, gravity might eventually overcome it. Expansion could slow, halt, and reverse, leading to a big crunch, where all matter collapses back into a singularity. Or perhaps dark energy could oscillate, producing cycles of expansion and contraction, a cosmic heartbeat echoing forever. The truth is, we do not yet know which of these futures awaits us. Observations of the cosmic microwave background, the distribution of galaxies, and the brightness of supernovae help constrain models. But the nature of dark energy remains hidden. It is the greatest unknown in modern cosmology, the blank space at the center of our equations. Philosophically, dark energy forces us to rethink our assumptions about nothingness. We once thought of empty space as truly empty. Now we know that even the void has properties, and those properties shape the destiny of everything. Emptiness is not passive, but active, a player in the cosmic drama. Dark energy also humbles us. For all our knowledge, most of the universe is composed of things we cannot see and do not understand. Dark matter and dark energy together make up 95% of reality, leaving only 5% for everything familiar. This means that our deepest insights, our greatest discoveries, are about a small fraction of what exists. Yet there is a strange beauty in this ignorance. Dark energy is not just a problem to be solved. It is also a promise that mystery still surrounds us, that the cosmos is deeper than we can yet fathom. In an age when we sometimes believe we have mapped all knowledge, dark energy reminds us that we are still at the beginning of discovery. So, what lies beyond the edge of the universe in the era of dark energy? The answer is expansion itself. Galaxies will continue to slip beyond our horizon, vanishing forever. The observable universe will shrink in terms of what we can see, even as the real universe grows larger. Future civilizations, billions of years from now, may see only their local group of galaxies, cut off from the wider cosmos by dark energy's relentless push. For us, standing here in the present, dark energy is a glimpse of eternity. It tells us that the universe is not a static stage, but a living, evolving entity. It whispers that the cosmos has a future as vast and strange as its past. And it challenges us to keep asking questions, to keep reaching beyond the horizon of knowledge. In the end, dark energy is not just a force, it is a mystery, written into the fabric of existence. It is the breath that carries galaxies apart, the silence that will one day swallow the stars, the unseen hand that shapes the destiny of all things. When people think of the end of the universe, they often imagine a fiery apocalypse, stars exploding, galaxies colliding, and everything consumed in chaos. But according to many cosmologists, the most likely fate of the cosmos is not fire, but silence. It is a future not of violence, but of exhaustion, a slow decline into darkness and cold. This is the heat-death scenario, and it represents one of the most sobering possibilities for what lies beyond the edge of cosmic time. To understand heat-death, we must return to a principle of physics called the second law of thermodynamics. This law states that in any closed system, entropy, often described as disorder, always increases. Energy naturally spreads out, moving from concentrated forms into diffuse ones. A hot cup of coffee cools as its heat spreads into the surrounding air. A candle flame burns out as its fuel is consumed and its heat dissipates. The universe, too, is governed by this law. In the early universe, energy was dense and concentrated. Matter and radiation were tightly packed. Stars formed abundantly, and galaxies blazed with light. But as billions of years passed, entropy increased. Stars converted hydrogen into helium and heavier elements, releasing energy as they burned. Supernovae scattered elements into space, fueling new generations of stars. Yet each cycle moved energy from usable forms into more diffuse ones. Today, stars continue to shine, but the process cannot last forever. Eventually, the supply of hydrogen will be exhausted. Stars like our Sun will expand into red giants, shed their outer layers, and leave behind white dwarfs. Larger stars will collapse into neutron stars or black holes. Once all stars have burned through their fuel, the universe will enter a new era, an era of stellar remnants. In this distant future, galaxies will be filled not with shining stars, but with the cold embers of white dwarfs, the dense husks of neutron stars, and the dark mouths of black holes. Without new fuel, no new stars will form. The night sky will grow dimmer, constellations fading as stars wink out one by one. But even that is not the end. White dwarfs will eventually cool to become black dwarfs, faint and frozen remnants radiating almost no heat. Neutron stars will persist, but inert, cold, and lifeless. Black holes will dominate, swallowing what remains of matter. Galaxies will decay as stars are flung out by gravitational interactions, leaving only black holes at their centers. And then comes the slowest process of all, the evaporation of black holes. According to Stephen Hawking's theory of Hawking radiation, black holes are not entirely black. They emit faint radiation due to quantum effects near their event horizons. Over unimaginable timescales, far longer than the current age of the universe, black holes will gradually lose mass and evaporate into nothing. When the last black hole evaporates, the universe will be left with only thin gas, stray particles, and low-energy radiation. Entropy will have reached its maximum. All energy will be spread so evenly that no work can be done, no stars can shine, no life can survive, no structures can form. The cosmos will be a uniform sea of darkness and silence. When we speak of the edge of the universe, it is easy to imagine it as something physical, like the edge of a table, the rim of a bow, or the horizon of the sea. Our language tempts us into thinking of sharp boundaries, solid walls, or cliffs of nothingness where the cosmos ends. Yet in truth, what we call the edge is not a physical structure at all. It is an illusion created by the limits of light, time, and perspective. This illusion begins with the speed of light. Light is fast, unimaginably so, but it is not infinite. It takes time to travel across distances. When we look at the moon, we see it as it was a little more than 1 second ago. When we look at the sun, we see it as it was around 8 minutes ago. When we look at the Andromeda galaxy, we see it as it was more than 2 million years ago. With every step farther into the universe, we are peering deeper into the past. Because the universe has a finite age, about 13.5 billion years, we can only see as far as light has had time to travel since the Big Bang. That limit defines the observable universe. Beyond it, the light from distant galaxies has not yet reached us. Thus, the edge we perceive is not the edge of the cosmos, but the edge of visibility. This already makes the edge an illusion. It is like standing in a foggy forest. The fog limits how far you can see, but the forest does not end at the fog's wall. It continues beyond your sight. In the same way, the universe continues beyond the observable horizon. The edge we see is not a true edge, but a horizon of perception. But the illusion deepens. Because space itself is expanding. Galaxies are being carried away from us. Some are receding faster than the speed of light. This does not violate relativity, because it is space itself that expands, not the galaxies moving through it, but it means that many galaxies are already forever beyond our reach. We can see their ancient light emitted billions of years ago, but we will never see them as they are now. They have already sailed over the horizon of no return. So the edge we see is doubly illusory. First, because it is only the limit of light's journey through time. Second, because much of what we see is already gone beyond reach, visible only in memory. The galaxies we observe at the edge are ghosts, their present selves forever hidden. There is also the illusion of direction. When we look out into space, it seems as though we are at the center of a vast sphere, with galaxies stretching away in every direction. But this, too, is perspective. Every observer, no matter where they are in the universe, sees themselves at the center of their own observable sphere. The edge is not a special boundary around us, but a horizon that exists for every observer. There is no true center, no privileged point, only an endless tapestry where each observer sees their own circle of vision. This makes the observable edge a profoundly human construct. It is not written into the universe, but into the nature of our observation. It tells us more about the limits of our perception than about the limits of reality. Even the concept of time contributes to the illusion. Because light takes so long to reach us, the edge of the observable universe is also the edge of the past. When we look far away, we are not seeing things as they are, but as they were. The edge is really a time horizon, a limit beyond which the past cannot be revealed. What lies beyond is not unknown space, but unknown time. In this sense, the edge is a mirror of our ignorance. It is not a place we could travel to or touch. It is a boundary drawn by physics, marking the point where information cannot reach us. It is the edge of knowledge, not the edge of existence. Philosophically, this raises profound questions. If the edge is an illusion, then what does it mean to speak of the size of the universe? We can measure the observable universe, but beyond that, we cannot measure. The cosmos may be finite or infinite, curved or flat, bounded or unbounded. Our edge gives us no answer. It is like being a sailor in ancient times, standing on the shore and seeing only to the horizon. The sea may end, or it may stretch forever, but the horizon reveals only the limit of sight, not the true shape of the ocean. When science speaks of the edge of the universe, it draws lines with equations, light cones, and the physics of expansion. But long before telescopes and satellites, human beings asked the same question in other ways. What is beyond what we can see? What lies past the stars? Is there an end, or is there infinity? These questions belong not only to physics, but also to philosophy. For the cosmos has always been more than a physical space. It has been a mirror for human thought, a canvas on which cultures, religions, and philosophies project their visions of reality. In ancient Greece, philosophers debated whether the cosmos was finite or infinite. Aristotle imagined a universe enclosed by celestial spheres with Earth at the center. For him, the heavens were finite, orderly, and eternal, ruled by perfect geometry. Yet other thinkers, like Democritus, argued for an infinite cosmos filled with countless worlds beyond our own. Even then, the question of edges divided human thought between finitude and infinity. In India, Hindu cosmology described a universe that moved in vast cycles of creation and destruction. Time itself was seen as circular, with no absolute beginning or end. The cosmos expands and contracts. Gods create and dissolve worlds, and existence is eternal. Buddhist cosmology also imagined infinite world systems, each with its own cycle of birth and decay. Here, the edge of the universe was not a physical boundary, but a limit of perception, for infinity meant that no one world was unique or final. In the Abrahamic traditions, the universe was often seen as finite, created by God at a moment in time. Beyond the stars lay heaven, and beyond heaven lay the divine. Here, the edge of the cosmos was not a horizon of physics, but a threshold into the spiritual. The edge was the place where creation touched the creator, where matter gave way to the eternal. Philosophy has also wrestled with the concept of nothing. Parmenides argued that nothing cannot exist, for to speak of it is already to make it something. Yet others, like Lucretius, envisioned the universe as infinite space, with no walls or ends. "Throw a spear," he said. "If it flies outward, then space continues. If it is stopped, there must be something beyond to stop it, which itself is part of reality." Thus, he concluded, space must be infinite. This ancient thought experiment still echoes in cosmology today. In the Middle Ages, thinkers like Thomas Aquinas tried to reconcile faith and reason. He argued that the universe might have a beginning or might be eternal, but either way, it required God as its ground of being. Here, the edge was not physical, but metaphysical. The question of why there is something rather than nothing. Modern philosophy, shaped by science, often shifts the question. Immanuel Kant argued that the human mind cannot truly grasp infinity or finitude on cosmic scales. If we imagine a finite universe, we are forced to ask what lies beyond, which leads us back to infinity. If we imagine an infinite universe, we are forced to confront the impossibility of perceiving it. For Kant, the edge of the universe reveals the limits of human reason itself. In the 20th century, existentialist thinkers like Albert Camus and Jean-Paul Sartre found in the universe's vastness a symbol of absurdity. The cosmos is silent, indifferent, perhaps infinite. Human beings, tiny and fragile, search for meaning in a reality that may have none. Here, the edge of the universe becomes a metaphor for the edge of meaning, the boundary beyond which human purpose dissolves. At the same time, cosmologists like Carl Sagan reminded us that the vastness is not absurd, but awe-inspiring. The fact that we can ask these questions, that we can map billions of galaxies and measure the age of the cosmos, is itself miraculous. Sagan saw in the infinite not despair, but wonder. "We are a way for the cosmos to know itself," he wrote. The edge of the universe, then, is not a wall, but an invitation to curiosity. When human beings gaze at the night sky, we are not just looking at stars, we are looking at possibility. Since the first fires lit in caves, since the first telescopes turned skyward, we have dreamed of going farther, of reaching beyond the horizon, of touching the unknown. Yet, as much as imagination soars, we remain bound by technology, by physics, by the very laws of nature. When we ask what lies beyond the edge of the universe, we must also ask another question. Can we ever hope to reach it, or even glimpse it, with the tools we create? Our first tool was vision itself. Eyes evolved to see light in a narrow band, a tiny sliver of the electromagnetic spectrum. For thousands of years, this was our only window into the cosmos. The stars seemed fixed, eternal, set in crystalline spheres. Then came the telescope, and suddenly the heavens expanded. Galileo's small tube of glass revealed moons around Jupiter, phases of Venus, and countless stars unseen before. The edge of the universe grew farther with every improvement in lenses and mirrors. But telescopes face limits. They cannot see beyond the cosmic fog of the early universe. About 380,000 years after the Big Bang, the universe cooled enough for atoms to form, allowing light to travel freely. Before that, the cosmos was opaque, filled with a plasma that scattered photons. No telescope, no matter how powerful, can see beyond that curtain. We can detect the glow of the cosmic microwave background, but the true first moments remain hidden. To probe deeper, scientists turn to other messengers: neutrinos, gravitational waves, particles that may have slipped through the early plasma. Detectors like IceCube at the South Pole or LIGO in the United States attempt to catch these elusive signals. They offer glimpses of the universe beyond light, windows into epochs otherwise invisible. But even these instruments have limits. The farther back we peer, the more faint the signals become, the more noise overwhelms them. Then there is the limit of distance. The observable universe stretches about 46 billion light-years in every direction, but much of it will forever remain unreachable. Galaxies beyond the cosmic event horizon are receding faster than light because space itself expands. No spacecraft, no signal can ever cross that gap. Even if we built ships that travel near the speed of light, the expansion of space would carry those galaxies away faster than we could approach. They are already lost to us. Within our own galaxy, technology offers hope, but also challenge. The fastest spacecraft ever built, Voyager 1, launched in the 1970s, has taken more than 4 decades to travel a distance of just over 150 astronomical units. That is still less than a light day from Earth. The nearest star beyond the Sun lies over 4 light-years away. At Voyager's speed, it would take tens of thousands of years to arrive. To dream of interstellar travel, scientists imagine technologies far beyond our current reach. Fusion drives, antimatter engines, light sails pushed by lasers. Some speculate about warp drives, bending space itself to move faster than light. Yet each faces immense barriers of physics and engineering. Antimatter is almost impossible to produce in useful quantities. Fusion remains elusive in controlled form. Warp drives may require negative energy, something not yet proven to exist. The edge of exploration is not only physical but economic. Building telescopes like the James Webb Space Telescope costs billions of dollars. Constructing interstellar craft would demand resources beyond what any nation has yet committed. Human ambition is vast, but human budgets are finite. There is also the limit of time. Even if we solved propulsion, interstellar journeys would take centuries, millennia, perhaps longer. Civilizations rise and fall in shorter spans. Can humanity sustain a mission whose success lies beyond the lives of countless generations? Some dream of generational ships, vast vessels where people live, die, and are born as the craft sails between stars. Others imagine suspended animation or digital consciousness, minds preserved for the long voyage. Yet each is speculation, still untested. And then there is the ultimate barrier, the speed of light. Relativity tells us that nothing with mass can move faster than light. As an object approaches light speed, its energy requirements rise without limit. Unless new physics overturns this law, faster than light travel remains impossible. This sets a hard horizon for exploration. We may dream of reaching the stars, perhaps even neighboring galaxies, but the edge of the universe itself will always lie beyond us. But limits do not end dreams, they shape them. We cannot fly with wings like birds, yet we learn to soar with engines. We cannot swim like fish, yet we cross oceans with ships. Perhaps the same will be true of the stars. Each limit is a challenge, an invitation to innovate. Philosophically, technological limits remind us of humility. We may never touch the edge of the universe, but we can still reach farther than before. Each generation extends the horizon, from Galileo's telescope to Hubble's deep field to Webb's infrared eyes. Each step shows that what once seemed unreachable can become known. Perhaps the true frontier is not distance, but knowledge. We may never travel beyond the observable universe, but we can model it, simulate it, understand it with equations. Our minds, aided by technology, can journey farther than our bodies. In that sense, we already explore beyond the edge every time we imagine the multiverse, higher dimensions, or cyclic time. And so, when we ask what lies beyond the universe, we must admit that our technology may never take us there. The limits of light, of speed, of energy, of time may forever block the path, but that does not diminish the wonder. It only makes the questions deeper. The edge of the universe may be unreachable, but it is not unthinkable. Through thought, through science, through philosophy, we extend our reach beyond what our hands can touch. Technology may set boundaries, but imagination pushes past them. Before science built telescopes and equations, before physicists spoke of horizons and expansion, human beings still looked upward and wondered what lay beyond the stars. Every culture, every civilization created myths, stories, and visions to explain the vast unknown. In these tales, the edge of the universe was never empty. It was filled with gods, monsters, paradises, and realms of mystery. These cultural and mythological visions of the beyond reveal not only our fear of the unknown, but also our longing to give it meaning. In ancient Mesopotamia, one of the first civilizations to map the heavens, the sky was imagined as a great dome arching over the earth. Beyond this dome lay the waters of chaos, the primordial sea from which creation had been carved. The Babylonian creation epic, the Enuma Elish, described how the god Marduk split the body of the chaos dragon Tiamat in two, using one half to form the heavens. In this vision, the edge of the universe was not emptiness, but the corpse of chaos itself, forever holding back the waters beyond. In ancient Egypt, the sky was imagined as the goddess Nut, arching her body over the earth, god Geb. Stars were jewels in her flesh, and each night she swallowed the sun, only to give birth to it again at dawn. Beyond the sky lay the realm of the afterlife, the Duat, a place of trials, monsters, and judgment. The edge of the universe was not just physical but moral. It was the gateway through which souls passed to face the scales of Ma'at, weighed against the feather of truth. In Greek mythology, the cosmos was ordered in layers. Above the earth lay the sky, and beyond the sky lay the ether, the pure realm of the gods. Beneath the earth lay Tartarus, a pit deeper than the heavens were high. The poet Hesiod wrote of chaos as the first principle, from which earth, Tartarus, and Eros emerged. The edge of the universe was chaos itself, a yawning gap that predated creation. And yet, Greek thinkers also speculated about infinity. Democritus and Epicurus spoke of infinite atoms, moving in infinite space, colliding to form countless worlds. Here, myth blurred into philosophy, and the beyond became an endless cosmos. In Norse mythology, the universe was envisioned as Yggdrasil, the world tree, whose roots and branches connected 9 realms. Midgard, the realm of humans, was only one of them. Beyond lay Asgard, home of the gods, Jotunheim, land of the giants, Niflheim of ice, Muspelheim of fire, and others. At the edges of the cosmos lurked the great serpent Jormungandr, encircling the world at Ragnarok, the end of time. The serpent would rise, chaos would break free, and the tree would burn. Here, the edge of the universe was both physical and mythic, a place of monsters and destiny. In Hindu cosmology, the universe is vast and cyclic. It is said to expand and contract through kalpas, immense ages lasting billions of years. Beyond the manifest world lies the unmanifest, Prakriti, the primordial potential. Gods like Vishnu are described as dreaming universes into being, with each breath creating and dissolving countless worlds. The edge of the universe is not a wall, but a transition between cycles, between creation and dissolution, between the waking and dreaming of the divine. In Buddhist cosmology, the universe contains countless world systems, each with its own Mount Meru at the center, surrounded by oceans, continents, and heavens. Beyond them lie further world systems, stretching without end. Samsara, the cycle of birth and death, is infinite, without beginning or boundary. The edge of the universe is therefore unreachable, for existence itself is boundless. The only escape is nirvana, liberation beyond worlds, beyond cycles, beyond the universe itself. Indigenous cultures, too, imagined edges and beyonds. Many Native American traditions spoke of layered worlds. The Hopi described an underworld from which humanity emerged, guided by the Creator. The Lakota envisioned the sky as a great tent, its poles anchored to the earth. Beyond lay the spirit world, inhabited by ancestors and powers. The Australian Aboriginal Dreamtime described the universe as interwoven with ancestral beings whose actions shaped both land and sky. For these cultures, the edge of the universe was not distant stars, but the boundary between the seen and the unseen, between waking life and the spirit realm. In medieval Europe, Christian cosmology placed Earth at the center, surrounded by spheres carrying the moon, planets, and stars. Beyond the fixed stars lay the primum mobile, and beyond that, the empyrean, the realm of God and angels. Here, the edge of the universe was the divine presence itself, eternal and perfect. Dante's Divine Comedy described ascending through the spheres to behold God as a radiant point of light beyond all comprehension. In Islamic tradition, the cosmos was also layered, with 7 heavens above and 7 earths below. Each heaven was ruled by angels, with the highest nearest to God. The edge of the universe was Al-Ghaib, the unseen, known only to God. The Quran speaks of the heavens being rolled up like a scroll at the end of time, and of creation being remade. Here, the beyond was both mystery and destiny, held within divine will. These myths and visions share a common theme. The edge of the universe is never nothing. It is chaos or divinity, monsters or gods, cycles or spirits. It is always something, always meaningful, always a reflection of human hopes and fears. Long before physics described galaxies, before mathematics measured expansion, before satellites mapped the cosmic microwave background, human beings imagined what lay beyond the stars. Imagination was our first telescope, our first equation, our first probe into the unknown. And even now, When science has given us vast data sets and precise models, imagination remains essential. Without it, no theory would be born, no experiment would be designed, and no vision of the beyond would ever inspire exploration. Imagination begins with awe. When ancient people stood under the night sky, they did not see data points or redshifts. They saw mystery. They connected stars into patterns, hunters, bears, ships, dragons, and filled the darkness with gods and stories. These constellations were the first attempts to map infinity, to make sense of the unfathomable. In doing so, people extended their minds beyond what their senses could reach. Imagination is also the bridge between observation and explanation. Galileo looked through his telescope and saw the moons of Jupiter circling their planet. But it took imagination to conclude that these were worlds in motion, challenging the belief that everything circled Earth. Newton watched an apple fall and imagined that the same force pulling the apple also held the moon in orbit. Einstein pictured riding on a beam of light, and from that thought experiment came relativity. In each case, imagination carried the mind beyond immediate experience into realms unseen. When we speak of the edge of the universe, imagination becomes even more vital. By definition, the edge is beyond observation. We cannot see what lies outside the observable horizon. We can only imagine, guided by theory, inflationary cosmology, multiverse hypotheses, higher dimensions. These are products of imagination disciplined by mathematics. They are not fantasies because they rest on equations and evidence, but they are also not directly observed. Imagination fills the gap. Human imagination also shapes the metaphors we use to understand the cosmos. We imagine the universe as a balloon expanding, as foam bubbling, as a fabric stretching. None of these are literally true, yet each helps us grasp a truth. Imagination provides the pictures our minds need to handle abstract concepts. Without it, physics would remain locked in symbols too cold for human comprehension. And imagination gives meaning. Science can describe expansion, entropy, dark energy, but imagination interprets these facts into stories. We imagine the universe as a phoenix, dying and reborn in cycles. We imagine it as a book, each universe a page in an infinite volume. We imagine it as a journey, with humanity sailing outward like explorers on an endless sea. These stories do not change the physics, but they change how we live with it. They make the infinite bearable, the unknown inspiring, rather than terrifying. The role of imagination is not only individual, but collective. Cultures share visions of the cosmos, and these visions shape identity. For the ancient Egyptians, the sky goddess Nut arching over Earth was not just myth, but a worldview. For medieval Europe, the layered heavens culminating in God's realm defined both cosmology and theology. Today, images from the Hubble Deep Field or the James Webb Space Telescope function in much the same way. They are cultural icons, shared visions that inspire not just scientists, but all who gaze at them. In art and literature, imagination of the cosmos has been boundless. From the Epic of Gilgamesh to Dante's Divine Comedy, from Milton's Paradise Lost to modern science fiction, writers have filled the beyond with gods, demons, aliens, and infinite worlds. These works reflect not only speculation, but also human longing, the desire for meaning, the fear of mortality, the hope of transcendence. Every imagined cosmos is also a mirror of the human soul. Even in science, imagination sometimes outruns data. Physicists imagine wormholes, warp drives, time travel, parallel universes. Many of these remain speculative, perhaps impossible. Yet, imagination drives the questions that lead to discovery. Without it, we would never search. The boundary between science and fiction is porous, with imagination flowing both ways. Critics may dismiss imagination as fanciful, but history shows otherwise. Imagination does not replace evidence, but it points the way. When Maxwell imagined fields filling space, it seemed abstract. Today, electromagnetism powers our world. When early astronomers imagined unseen planets tugging on orbits, they later discovered Neptune. Imagination precedes observation, laying tracks for discovery to follow, but imagination also has limits. It can mislead as well as inspire. For centuries, people imagined the heavens as perfect spheres, and this delayed the acceptance of heliocentrism. People imagined Earth as flat, and this hindered exploration. Imagination must always be tested by reality, and without discipline, it becomes fantasy, detached from truth. The challenge is balance, to imagine boldly, but to test rigorously. Philosophically, imagination is part of what it means to be human. No other species, as far as we know, imagines the edge of the universe. Birds migrate by instinct, apes use tools by learning, but only humans imagine infinity, nothingness, parallel worlds. This capacity defines us. It allows us to live in two worlds at once, the world of what is and the world of what might be. And imagination connects us to the future. The tools that will explore the cosmos tomorrow begin as dreams today. Spacecraft, telescopes, quantum computers, all were once ideas in someone's mind. Imagination is the seed of technology, the blueprint of progress. When we imagine traveling to other stars, we plant the possibility of doing so. So, what lies beyond the edge of the universe? The scientific answers are many. More galaxies, other universes, quantum foam, heat death. But behind all these answers lies imagination. Without it, we would not even be able to ask the question. Perhaps then the greatest role of imagination is not in giving us answers, but in keeping the question alive. The edge of the universe is not a wall to be reached, but a horizon to be pursued. As long as we imagine what lies beyond, we remain explorers, even if we never leave Earth. In the end, imagination ensures that the cosmos will never feel empty. The stars may be cold, the distance is vast, the universe indifferent, but imagination fills it with meaning. It turns silence into story, darkness into wonder, the edge into a beginning rather than an end. And so, imagination is itself a kind of universe, boundless, expanding, filled with possibilities. It is the inner cosmos that mirrors the outer one. And when we look up and ask what lies beyond the edge, we are really listening to the echo of our own imagination, stretching out as far as the galaxies, as far as time, as far as infinity itself. We have journeyed far, from the birth of the cosmos to the horizons of perception, from quantum foam to heat death, from ancient myths to modern equations. With every step, the question has remained the same. What lies beyond the edge of the universe? And with every step, the answer has grown more elusive, more layered, more profound. Now, as we reach the end of this long exploration, it is time to reflect on what it means to live with such a question that may never have a final answer. The first lesson is humility. For most of history, humanity believed the cosmos was small and centered around us. Earth stood at the middle, the sun and stars circled in neat spheres, and the edge of the universe was a clear, knowable boundary. Then discoveries shattered this vision. Earth became one planet among many, the sun one star among billions, the galaxy one among trillions. With each revelation, the edge receded. The universe grew vaster, and our place within it grew smaller. Humility is not optional. It is written into the structure of reality itself. The second lesson is wonder. If humility shows us our smallness, wonder shows us our greatness. For in all the immensity, in all the silence, here we are, beings who ask, beings who imagine, beings who explore. The universe may be infinite, indifferent, and cold, but it has given rise to consciousness capable of reflecting on it. When we ask about the edge of the universe, we are not just gathering facts, we are participating in the grandest act of wonder that existence allows. The third lesson is impermanence. The cosmos itself is a story of change. Galaxies form and drift apart. Stars ignite and die. Black holes grow and fade. Even space and time are not eternal in their present form. Whether the future brings heat, death, big rip, or cosmic rebirth, our universe will not last forever. Living with this truth means accepting that everything is temporary, yet also that impermanence is the very reason anything exists at all. Without change, there would be no stars, no worlds, no life, no us. The fourth lesson is imagination. The edge of the universe is not a place we can travel to, but a horizon of thought. When we imagine what lies beyond other universes, higher dimensions, divine realms, cycles of rebirth, we are not escaping reality, but engaging with it. Imagination is how science advances, how culture thrives, how humanity grows. The unknown is not just a void, but a canvas for imagination to paint upon. The fifth lesson is acceptance. There are limits we cannot cross. The speed of light, the horizon of visibility, the opacity of the early universe, these are barriers built into the laws of physics. Perhaps there will always be mysteries that remain forever beyond us. Acceptance does not mean giving up. It means finding peace with uncertainty, learning to live without final answers. The unknown does not diminish us. It deepens us. It teaches us to live in a universe that is always larger than our grasp. The sixth lesson is meaning. The edge of the universe is not only a physical boundary, but a metaphor. It represents the limits of knowledge, the boundaries of life, the horizon of death. Every human being faces their own edge, the unknown of mortality. In contemplating the cosmic edge, we also contemplate our own. What lies beyond life, beyond consciousness, beyond existence, we do not know. And yet, we live, we love, we create, knowing that we cannot know. The cosmic edge becomes a mirror for the human condition. To live with the unknown, then, is not despair, but wisdom. It is to walk to the horizon, knowing it will recede, and still keep walking. It is to sail into seas that never end, not to arrive, but to journey. It is to ask questions, not because they will be answered, but because asking them is what makes us human. So, what lies beyond the edge of the universe? The honest answer is this: we do not know. Perhaps more galaxies, stretching into infinity, perhaps other universes, each with different laws. Perhaps cycles of death and rebirth, phoenix after phoenix rising from ashes, perhaps nothing at all, a silence beyond comprehension. Or perhaps the question itself has no meaning, because the universe has no edge to begin with, and that is the final lesson, that the unknown is not a problem to be solved, but a condition to be embraced. The universe will always be larger, deeper, stranger than we can imagine. But that is not a failure. It is a gift. It means there will always be mystery, always be wonder, always be horizons to chase. As Carl Sagan once said, "We are star stuff, contemplating the stars. We are fragments of the cosmos that have become conscious, looking back at the whole and asking what lies beyond." No matter how far science goes, no matter how many answers we find, that act of wonder will remain. To live with the unknown is to live fully in the present, to marvel at the beauty we can see, to accept the mystery we cannot, and to keep imagining the beyond. For the edge of the universe is not the end of the story, it is the beginning of every question. And perhaps, in the end, that is the truest answer of all. What lies beyond the edge of the universe? More mystery, more wonder, more unknown. And it is in that unknown that humanity finds its deepest calling to explore, to imagine, and to live.